In this video, we're going to look at the differentiability of a function in a specific point. But before you understand the differentiability of a function, it's very important that you understand the continuity of a function. So make sure that you watch the video on limits and continuity first. But if we look at the differentiability of functions, let's look at the definition first. The definition states that if a function is differentiable at x is equal to a, then f of x is also continuous in that point. So if it's differentiable, then it is continuous. It's not necessarily the same in reverse. So a function may be continuous, but not necessarily differentiable. So if you want to prove if a function is differentiable at a specific point where x is equal to a, you must prove that continuity exists, or it must be stated in the question. Let's look at this question, and we want to know, is f of x differentiable at x is equal to 2? Before we can decide if it's differentiable, we need to decide if it's continuous. So we are going to examine the limit as x approaches 2 from the left-hand side. And if we approach 2 from the left-hand side, we're going to use the first equation. And if we substitute 2 into that equation, we end up with 3. The limit as x approaches 2 from the right-hand side, we're going to use the second equation. And if I substitute 2 into that equation, we also end up with 3. So the limit from the left is exactly the same as the limit from the right. So the limit exists. So we need to go on and establish what is the value of the function in the specific point. And that top equation is where x is smaller than and equal to 2. Now, even though we've used that equation before, that was to decide on the limit as we approached 2 from the left. Now we're using the exact same equation because x is smaller than or equal to 2 along that line. We have to use the equation again. So we have to show that substitution again. So the function value at x is equal to 2 will be 2 plus 1, so it's 3. So because the limit as x approaches 2 from both sides is the same as the function value at x is equal to 2, the function is continuous at x is equal to 2. So now that we've established that it's continuous, we can go on and see if it's differentiable. So first thing we need to do is find the derivative of f of x. The derivative of x plus 1 is just 1, and the derivative of 2x minus 1 is 2. So the derivative of x is 1, where x is smaller than or equal to 2, and the derivative of f of x is 2, where x is greater than 2. So if we want to know the derivative as we approach 2 from the left-hand side, in other words, the limit as x approaches 2 of the derivative, well, there's nowhere to substitute that value of x, so it's just equal to 1. And the limit as we approach 2 from the positive side of the derivative of x is 2. Now those two values are not the same, so the limit as we approach x is equal to 2 from the negative side of the derivative is not the same as the limit as x approaches 2 from the right-hand side. In other words, the limit of the derivative does not exist, so it is not differentiable at x is equal to 2. Let's look at another example. Is f of x differentiable at x is equal to 1? We first want to test if it's continuous at x is equal to 1. So if we have a look at the limit as x approaches 1 from the negative side, we're going to use the top equation, so x plus 1. So if we substitute 1 into that equation, we end up with 2. Then the limit as x approaches 1 from the right-hand side, we're going to use the second equation. And 1 squared is 1. So because the limit from the left-hand side does not equal the limit from the right-hand side, that limit does not exist. And if the limit does not exist, then the function is not continuous at x is equal to 1. So because the function is not continuous, there's absolutely no way it can be differentiable at the point. In example 3, we're looking at differentiability in a slightly different way, and it's a very important question for exam purposes. So we need to determine the values of a and b if f of x is differentiable at x is equal to 1. Now, if it's stated that the function is differentiable at x is equal to 1, it means that the limit of the derivative as x approaches 1 from the left-hand side is the same as the limit of the derivative as x approaches 1 from the positive side. So we want the derivative as x approaches 1 from the negative side. So we want the derivative of x squared plus 3x plus a. And the derivative is 2x plus 3. So the limit as x approaches 1 from the negative side is 2x plus 3. And then the derivative of bx plus 2 is just b. Now, what else do we know about that point? Where are we trying to test differentiability? We're trying to test it at x is equal to 1. So we're going to substitute x with 1. In other words, we end up with b is 5. So we managed to calculate the value of b. How can we calculate the value of a? Well, remember, a function is only differentiable if it is continuous. So because it was stated in the question that f of x is differentiable, we can also assume, or it implies, that f of x is continuous at x is equal to 1. So if a function is continuous, the limit as we approach 1 from the negative side of f of x will be the same as the limit as we approach 1 from the positive side of f of x. So in the first part of the answer, we dealt with the derivative, and now we're dealing with f of x. So if we look at the left-hand side, it implies that x squared plus 3x plus a is equal to bx plus 2, or the limits in those points. So how can we take it one step further? Well, we know that b is equal to 5 and x is equal to 1, so we can substitute those values in, and we end up with 1 plus 3 plus a, or 4 plus a, is equal to 5 plus 2. And if we take 4 over to the other side, it ends up with a is equal to 3. So we've managed to determine the values of a and b. So remember, if it's stated that a function is differentiable, we can assume that this implies that the function is also continuous at x equals 1. Thanks for watching Max Maths. If you liked what you saw, please like, share, and subscribe.